Welcome to this new online class on graph partitioning and expanders. This will be a research-oriented graduate class on material that I liked a lot the first time that I learned it, and I hope that you're going to love it at least as much during this course. My plan for this first week of class is to start from a summary of the main topics of this course, and then we will start working on technical material, and we will study spectral graph theory, which is a collection of techniques on how to solve graph problems by using linear algebra. Today we will see one of the fundamental theorems of spectral graph theory, which will say that if we know the eigenvalues of the adjacency matrix of a given graph, then there are a lot of properties of the graph that we can deduce just by looking at those numbers, including whether or not the graph is bipartite, whether or not the graph is connected, if it's not connected, how many connected components there are, and so on. So the main topics of this course will be, first, a study of approximation algorithms for certain graph partitioning and graph clustering problems. The main problem that we will look at is that suppose that in a given graph there is some subset of vertices such that almost all the edges incident on those vertices are entirely contained inside the set, and very few of the edges comparatively leave the set. Can we find such a set? And if there are many such sets that are disjoint, can we find many of them or all of them? So then in the second part of the course, we will look at the problem of constructing expander graphs. Expander graphs are graphs with very strong connectivity properties. They are in many ways similar to random sparse graphs, even though they're not random at all, they're just graphs coming from a well-defined construction. And they have lots of applications. They're useful to design algorithms, data structures, error correcting codes, cryptographic protocols, and so on. But they're very difficult to construct, and we will see a couple of approaches to construct them. Then, in the third part of the course, we will look at the problem of estimating the convergence time of random walks in graphs. This is a huge area of research that has a lot of applications. We will focus on one particular computer science application, which is the study of the convergence time of certain randomized algorithms. It's a study that can be reduced to the study of the convergence time of random walks on certain graphs. So these three topics seem to be pretty unrelated to each other. And in fact, they are studied by three fairly different communities. However, there is a lot of mathematics in common between these three areas. They all, in very different ways, look at questions about expansion of certain graphs. And they all use the mathematics of spectral graph theory, which we will start studying today. And there are a lot of advantages in looking at these three topics all together, because those connections will become apparent. And studying similar mathematical concepts, but looking at them from three very different perspectives, will be very helpful. Let's start with the definition of expansion. And let's begin by looking at a concrete example of a graph that is not a good expander. So suppose that this graph describes the topology of a communication network. Well then, one way in which this would be an unreliable communication network is that if these two edges happen to fail, then this half of the vertices become unreachable from this other half of the vertices. So in general, in a cycle with n vertices and edges, you may have just two edges fail, and at the same time this could cause as many as n over 2 vertices becoming unreachable from the rest of the graph. So in general, in the expansion problem, we will be looking at whether or not in a graph there exist large sets of vertices such that they can be disconnected from the rest of the graph by the removal of a relatively small number of edges. So let's give the precise definition. Let's say that G is an undirected graph in the entire course we will almost exclusively look at undirected graphs. And let's say for now that it's d-regular. So if this is the set of vertices, let's look at some cut dividing the set of vertices into set S and its complement. And let's look at the number of edges going across. So this will be a non-expanding cut if the number of edges crossing over is small compared both to S and to S complement. So we'll say that the expansion of S is the number of edges crossing this cut, which we will write as ES S complement, divided by d, which is the degree of the graph, times the size of S. So there are a few equivalent ways of thinking about this definition. One is that d times S is a trivial upper bound to the number of edges that we need to remove from the graph in order from S to become disconnected from the rest of the graph. And so here we are measuring how much smaller is the actual number of edges that we need to remove to disconnect S from the rest of the graph compared to this trivial upper bound. Another way to think about it is that we may perform the following probabilistic process. We pick uniformly at random an element of S, and then we move at random to one of its d neighbors, again uniformly at random. So maybe S has these 3 neighbors and we pick this one. Well, then the expansion of S is precisely the probability under this distribution that we end up with a vertex not in S, because the choice of the initial vertex we had 6 equally likely choices. For the choice of the random neighbor we had d equally likely choices. So that's the whole size of the sample space. And then the number of choices that make us end up into S complement is precisely the number of edges with one endpoint in S and one endpoint in S complement. So this is the probability. Then we define the expansion of a graph to be the minimum over all subset of vertices are non-empty, and that correspond to the smaller side of a cut, so they contain at most half of the vertices of the expansion of S. So this will be the optimization problem that we will be interested in solving in graphs. And as well, we will also be interested in understanding for what kind of graphs the optimum of this optimization problem is large. So let's see a couple of examples. We've already seen the example of a cycle. So in a cycle, the number of edges that cross a cut like this is 2, and we divide it by the degree times, so if this is S has n over 2 vertices. So the expansion of this set S is 2 divided by n. And in fact, this is the optimal expansion for this graph. So these cycles are families of graphs where the expansion goes to 0, and it goes to 0 fairly quickly with the number of vertices. Let's see another example. Let's say we have the Petersen graph. This is a graph that is 3 regular and has 10 vertices. Well, this choice of a set S contains 5 vertices, and there are 5 edges that cross between S and the complement of S. So the expansion of this set is 5, which is the number of crossing edges, divided by the degree times the size of S, which is also 5. So the whole thing is 1/3. Let's see just one more example. Suppose we have the cube. It's again a 3 regular graph. Here it's possible to show that this is a minimal cut. So let's see, in this cut there are 4 crossing edges, and there are 4 vertices in S, and the graph is 3 regular. So the expansion of this cut, which turns out to be the minimal expansion of all cuts, and so it's also the expansion of the graph, is 1/3. And indeed, in general, if you look at a k-dimensional hypercube, the expansion will be 1/k. So we have given a definition only for regular graphs. So here is a definition that will be the same as before in the regular case, but can be applied to arbitrary graphs. So let's say we have an arbitrary undirected graph. This is the number of vertices, and we have some cut. This is S, this is the complement of S, these are the crossing edges. So the just one more definition, we'll call the volume of a set of vertices the summation of the degrees of the vertices in the set. So if the graph is d regular, the volume of a set S is just d times the cardinality of S. So then the conductance of a set S is defined as the number of crossing edges divided by the volume of S. Notice that this is the same as the expansion if the graph is regular, because in that case this is the number of crossing edges divided by d times the cardinality of S. And then the conductance of G will be the minimum of this quantity over all the sets S for which we don't have a division by 0 here, and also such that when we look at the cut S V minus S, S is the low volume side of the cut. In terms of interpretations of this quantity, they are pretty similar to the ones that we gave for expansion. For a set S, the volume of S is a trivial upper bound to how many edges we need to remove from the graph in order to disconnect S from the rest of the graph. And so here we're looking at how much better than this trivial upper bound we can do if our goal is to separate S from the rest of the graph. And in terms of probabilistic interpretation, if we pick a random element of S with probability proportional to its degree, in the regular case this will be the uniform distribution, and then suppose you pick at random one of the neighbors, well then this ratio, the conductance of S, will be precisely the probability that this probabilistic process takes us outside of S. Because again, the volume of S is the size of the sample space, and the numerator here is the number of random choices that will take us outside of S. So these are the problems that we want to study, and let's see what those problems look like in some concrete examples of graphs, which will give some idea of what kind of solutions we're looking for to this problem, what kind of approximations will make